Hey there, welcome. My name is Chris Dale. This is a video demonstrating the challenge Natas 28 over at overthewire.org. Beautiful little war games and challenges helping us to demonstrate how to hack and basically a safe playground for learning how to hack and break into security systems. So let's search for something here. We got this little whack computer joke database here, and basically we can search for jokes, it looks like. What do computer science students use for birth control? Their personalities. That's a bird. How many programmers does it take to change a light bulb? None. It's a hardware problem. Yeah. If it weren't for C, we'd all be programming in BASIC and COBOL. So BASIC and COBOL. That's funny and also truth. Okay. So basically, we can look up jokes, right? We can search for stuff and we can find jokes. Funny thing is, when I just search for A, we get another joke. My daily unit command list is unzip, strip, touch. Okay. Okay, that's a dirty joke. But interesting thing is that when we search for the same thing, we are actually getting a randomized list of jokes here. So that kind of begs the question. We got a random list of jokes, and also we're only getting 3, so there's a limit 3 in here. Another thing to notice is that we're now at search.php. Here's index.php. Searching for something brings us into search.php, and here we have this query string, right? We have this query string that is obviously interesting. So this query string has URL encoded characters in it, %3d. This is going to be a base64 encoded string most likely. Let's do URL decode. Looking at the results, we see pluses, we see slashes, we see upper lowercase characters and also numbers, base64. And behind it, we basically have non-human readable data. We could do a 2hex and see if we can maybe recognize some of the bytes here to see if, like, is this like gzipped content, whatever. But right now it doesn't really look like human readable in any shape, form. So I'm not really into trying to break that right now. That is trying to break it with like some known patterns here. One thing we could do is we could try to attack the crypto itself using burp intruder, for example. So we could do a query here, for example, and we could just fuss this just like we would do anything else. So here we could just define a payload, go with URL code with special only bytes, remove this and add a URL decode because we are actually inside of a post parameter here. So I'm going to do URL decode instead of having these %00 and so on. And we could look for, like, we're just seeing a bunch of 302s, so they're redirecting us into search.php with the query parameter there. And we're looking for any type of 500, any big difference in content lengths. So here I have one that is 1263, and all the way up top 1273, so that's 10 bytes in difference. But it looks like it's just the query string here that's changing slightly. Alright, we could also fuss. There was also another script, right? There was a search here. We can also fuss this, Control I, center intruder. Here, we can fuss this one as well. So let's just do like this. Start attack. Now you see more interesting stuff. In fact, now you see request errors because my requests are not URL encoded, so we're breaking the queries here. So we should have been using URL encoding right now. What we're interested in is seeing if there's any 500 errors. 400 most likely not going to be interesting right now. And then from the 200, is there anyone looking differently? And we do have some that looks differently. This first one, for example, gives us a legit result because we are including a legit query string. Then on these we have incorrect amount of PKCS, number 7 padding. So we have padding here, and this padding basically means that we're looking at a block cipher. That's basically what we can conclude from this fact. The fact that we're seeing this error message, incorrect amount of PKCS 7 padding for block sizes, it means that it's a block cipher, it's not a stream cipher. Now, whenever we have block ciphers, we want to determine a few things. We want to determine, for example, size of blocks, offset of payload, and maybe even decode crack. Maybe. Depends. So let's start with the size of blocks. So in order to determine the size of the blocks, we will basically input a lot of data and see what we get out of it. So here we'll go back to the post and we'll do a brute force payload. Brute forcer here, capital A, minimum length 1 to 100. And this will basically cause my script here to just send 1A, 2As, 3As, 4As. And the reason I'm doing this is that I want to measure when this here, this encrypted string, this block cipher increases in size. And I'm not talking about minor increases like these 2 bytes here. I'm talking about a major increase in bytes. And we go down, and we can see from here, from 12 to 13, we actually have a ton more bytes being added. We have 14 bytes more added to this location here. So that's very interesting. So let's flag byte number 12. This one is very interesting. And then we go down and basically we count until the next increment comes. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16. So 16 is the byte length. 16 requests in between. The moment I hit something more than, the moment I hit 17 basically, I had an increase in the amount of data that I got back, and a substantial increase, meaning that we just had another block being encrypted for us by the back end. So that's interesting knowledge. Why don't we put that in our notepad? Size of blocks is 16. Now offset of payload. So we want to know when do we start a new block in here? How many A's can I put in until I know for a fact that I'm typing into a new block, for example? That's something very interesting to analyze. The first thing we're going to do is we're going to save this attack here. We're going to save it to file, attack.zip. So Burp Intruder saves it as zip files. I'll open up a command.cmd, cd into temp, and we'll unzip. Attack zip. And now we have a file called intruder. This intruder basically contains the entire attack, okay? And it's a binary file, contains a lot of bytes, but also has the ASCII inside of it. And what I'm gonna do is I'm gonna grep for this here, search.php. So I'm gonna grep for this. So grep for this, and it's a binary file, so let's convert it to, let's do an ASCII search. And just like that, we have all the locations, right? So we have all the results from the backend for our 100 different payloads right now. I'm now gonna cut field number 2 delimiter on the equal sign here, because that will allow me to grab only the payload instead of entire redirect header. So I'll take these. Notice that the first 2 are also duplicates. That's because the first one here is 1A, and also our first payload is 1A. So I'm gonna skip off the first one. Then, why don't I put this into our favorite tool, CyberChef, right? There are 3 favorite tools, Netcat, CyberChef, and Burpsuit. So we'll put this in here, and we want to decode this data. We want to decode. So let's do fork. So for each one of these lines, we're gonna do URL decode. So for each line, URL decode, and then basically for from. And now we have the data. And it's kind of interesting data. Especially here, see this? This is actually a repeating pattern. Let's go back to the application here. And let's search for a bunch of A's, okay? A bunch of A's. Let's see what I'm doing here. I'm gonna intercept this request. And I'm searching for a bunch of A's. And I'm also going to intercept the result here. So we now get a redirect. Let me analyze this redirect here, because this redirect here is going to include some interesting information. So here we go. Look at this repeating pattern. You see all these bytes here? See this repeating pattern? This is not the sign of a block cipher that is in cipher block chaining mode, this is the sign of a block cipher like ECB, electronic codebook cipher, where electronic codebook cipher will just reuse one key and encrypt the different blocks with the same key. Cipher block chaining mode will instead take all the different blocks and use the previous block as an initialization vector for the encryption of the new blocks. Hence, when you have in cipher block chaining mode operations or encryption operations, the repeating blocks won't have the same pattern. But with ciphers like electronic codebook cipher, you will actually see a repeating pattern here. Let me do something here. How can we better see the repeating pattern? Let's do regex here. Let's do 2hex, remove the spaces, and regex, regular expression, let's do find anything not 16 times but 32 times, because one byte is represented with 32 different hex characters here. So we'll do display total, and then we're gonna do list matches. Here we go. You see, this is one block, all right? This is one block, and this is another block. This is one block, this is one block. You see these? These all represent capital A. These all represent capital A. That's basically what they mean. So I can now take this data here, and I can go, say, notepad, and I can truncate all of them. I don't need them all in this example. I can say, hey, this represents A times 16. This represents something. This represents something. And this represents something. I don't know yet. And this also represents something. Sometimes with ECB mode ciphers, we can actually decrypt data following our input. That would be useful potentially. But we don't know these x's here. We know A times 16 because this is for a fact gonna be A's. But we saw that we had, we saw that we had multiple repeating blocks. That's interesting. So I'm gonna leave one more here so that we know that we have repeating blocks here. What I want to learn more about is what this is, and what this is, and potentially what this is. So let's take a look at our data here. Here we have all our data with all the different attacks that we copied before with the attack.zip, and we extracted it and so on. Let's do 2hex here. We have fork from, and then we have the patterns here. Let's do no, and let's figure out the blocks here. So regex again. We'll just do the same thing we just did in the previous example. 32 in size, display the total, and less list matches. So now you can see that we have up here, with a length of 1, we found 5 blocks. So this is 1A, right? In fact, why don't we do it like this? So all the way up top, I'm not going to do all of these here, but this is basically, this is 1XA. And then we have 2XA here, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. Oh, and this is where the block increments, so that's interesting. Does the total found start on top? Okay, so the total found starts on top. So, all right. So we're probably good from there. So 15, right? So I'm not gonna save more blocks than this. It would be interesting to take a look at some of the later ones, maybe when we have 8 blocks, for example, because I do expect us to have a repeating pattern here. Yes, as you can see here, F63. So we're gonna save that one. All right, so we have all of this. So this is gonna be 3, this is gonna be 4, and this is gonna be 5, 6, 7, 8, 9, 10, what? 11, 12, 13. Okay. So at 12 axis, we actually have another an increase in the blocks. I'm not sure why I couldn't count. 1, 2, 3, 4, 5, 6. Ooh. 7. Why can I not do this? Why is this so hard? I guess Maybe we should have used programming to do this instead to prevent these mistakes, but I'm a bit lazy programming wise right now. So here we go. All right, so total found 6. We went from 5 to 6 when we put in 13 A's. Okay, so that's 100% now. Now what I want to show you here is that first of all, when this block goes from 5 till 6, we add one more block. Where is that block being added? Well, what we could do then is basically check these blocks here. Look for this block. So Control C, Control F, and see where it is. Can I do highlight? Oh, there you go. So the first block is actually represented throughout all our payloads. You can see it up here. So this here, let's comment this out in the beginning here. So this is actually start. Same for all. Then we'll do the second one. Control F, Control V. And it looks to be the same for the second one. Start, same for all. And then, in fact, we can see it here as well. You see the third block here? The third block does not repeat itself. In fact, the third block changes all the time. You can see here, it changes all the time. So my question is, how most likely our data is inside this block. Most likely our data, our capital A's are filling up this block here. How many A's does it take to fill this block? And to determine that, all we got to do is figure out when this block starts to repeat. So here is 8816, here is 5422, here it is already now, 5422, 5422. This is when we are no longer putting in data here. This is where we start seeing a repeat. So start of repeat. You see 5F22. So that means that this is basically containing our capital A's. How many though? How many A's does it contain? We need to find the offset. That's one of the things that is very useful in breaking some of these cryptos. Finding the offset. How many characters am I inside of this string here until I break into a second block here? So we are inputting 10 A's. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see here another block being added at here. So this is where it repeats itself, and we're now starting to put stuff into here. And also keep in mind with crypto and block ciphers, there's actually padding going on. That's why you will see now these two here changing, because we're now putting in more A's. We're going to put them into the next block here. So with 10 A's, we're basically creating this pattern. 10 A's, that leaves us with 6 wildcards. 1, 2, 3, 4, 5, 6. These I don't know, and I'm not sure if I will be able to decrypt them either. But after these 10 A's, I'm basically seeing a repeating pattern. And if you were to try to track something later, like track the end of this cipher, you would basically remove this character here, add an X, and rotate all bytes possible for this X until you hit this value again, and that's how you know that you've actually hit and decrypted a byte. So you can actually decrypt ECB one byte at a time in many cases for the preceding, for the output coming after here, not the preceding output. So this is interesting. So after 10 A's, we got repeating pattern here, and after 12 A's here. So this is basically here. So after our 10 A's plus 2 A's, we are seeing that if you put in another one, you will receive a new block. So you will receive a new block. And how many blocks into this do you think it takes until it adds another block? Well, that's going to be 16. So we can do 1, 2, 3, 4. Yeah, I deleted a bunch of these, so let's just remove these, to be honest. That's probably gonna be fine. So it's gonna be 16 basically in between. All right. Crypto, huh? Fun. Let's see. We got a start of repeat. We got the string down here, bringing over a new block. One of the things that we did want to collect from the ones that I just deleted was the repeating pattern. Yes, here. I want to save this. Because what we're seeing here, so I don't need 14, 13, I believe. Let's remove these. So here we're actually seeing, so you see these blocks very clearly now. You see this 5F22, 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 and up here, 5F22 before 10, this third block is changing all the time based on our input. Very important thing to observe. And from here you see we have down here we have 875 until we get down to many A's. We actually have a repeating block here of all these capital A's, with seen by this F633E6B. So I think so far we're okay. What are we supposed to do in this challenge even, right? We are in a database trying to break in, and we could look for SQL, but we already fussed this. Very nice question, actually. How do they protect themselves against SQL injection? Because we would have discovered SQL injection most likely using a double quote or a slash or a parentheses or a quote earlier on when we did our fussing. So how do they protect themselves against SQL injection? How do they filter, or do they do some escaping, for example? What we could do is we could intercept. When we do 12 A's here, we could intercept a request with 12 A's, and we could change the last A and fuss the last A to see if it impacts at all the last block. Because the last block after 12 A's will actually be total found 6. So new blocks, new block here. So why don't we do this? What we'll do is we'll put into the repeater a request. For example, here, put this into repeater, and we'll do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's going to be 12, and that's going to give us a query string like this. Let's decode this query string just to see what's up. So this looks like it's okay. Here we have 5 blocks, and I'm just going to take notes of this. We'll do it here. So 12xa is this. Now we're going to do 13 A's. Send. And as we predicted, the block has increased with 1. So because we had 13 A's, we have 1 extra A. Sorry, 1 extra block. And this is the extra block. Now my question is, can I fuss the last A? So we do this, 12A, send it to the repeater, and then do the last A here. We're going to fuss it with all possible characters. No, special characters only. We're going to strip off URL encoding. And we're going to check to see if any one of these bytes that I put in result in a larger block. For example, here, how many blocks is this? Just going to quickly take this one out. Here we have 1, for example. So when we inputted a null byte here, we got an extra block of data. Now, null bytes can cause all kinds of significant computer security problems. Right now, I'm going to check to see if there's anyone else. And I think this is the gist of it. This is actually it. You see these 1271s? We're going to ignore all of these requests here. These we don't care. So we're fussing with all of these special characters here. But what about these ones with a content length higher up here? A null byte. This magic character here. This tab or character return, for example. Double quote, single quote, backslash. These characters here produces an extra block. Probably because they're adding a filter to some kind of SQL. So we are targeting a database here, right? That's what they're telling us. So what they're telling us is that they probably have some joke database. Whack computer joke database. So select joke maybe from my jokes where joke like equals whatever you're searching for, right? Something like this, semicolon. Where our input is probably inside of here. Most likely something like this. So if we were to inject into this, what we would do is probably something like this. Tick. But they don't like the ticks. So they protect the tick by a backslash. And then if you put in a double quote, they protect the double quote with a backslash. In fact, if you try to backslash the backslash to make it voided, they will backslash your backslash again to basically protect you against SQL injection. So what I'm thinking here is that we can input potentially a tick and cause the tick to be in the next block down here and cause the backslash to be a part of this block up here, and then overwrite the block that contains the backslash with a known good block. Sounds complicated? Sounds interesting? I hope so, because that's how you can attack ECB. These blocks that you encrypt, the blocks that the application returns, they're static. There's no change from what you have inputted before to what you're going to see later in the cipher blockchain. So they're all based on one static key, and that's a problem here. So for example, this string here, which I know represents, for example, this here, I know this represents some unknowns and capital A's. And then what follows is going to be my input. What I could potentially do is I could put in an input saying, for example, instead of these A's, what I would do is like tick union all select. And I would make sure that this tick comes at the end of this block, so that when they add the backslash in front of my tick, my union all select goes down to the next line. In fact, let's not do that. It goes down to the next block down here, like this. So the tick will still be there, the backslash will still be there, but once I have this done, I can maybe overwrite this block with a known good block. The block containing a backslash, I can overwrite with this block here, for example, that is a known good one, and most likely the attack will work. So what type of attacks would we be looking at? Well, we will be looking at something along the lines of, for example, tick union all select. And we don't really know a lot about this database. So let's do version. And then if there's multiple columns, not just joke, maybe something else as well, like an ID, we can do dash, comma, version, and so on to see if we can select more stuff. And then we do a semicolon hash to comment out the rest of this stuff. So our input is basically this, okay? This is going to be our input. Then we go to repeater, and we're going to count A's here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That sounds correct. Then we do tick, union all select at that version. All right, let's try to decode this and let's see what we got. Now I expect the third block now to be different. I don't expect to see the one that we saw before, the 5F22. But I do see that 5F22. So why is that? Because, one more time, 12x fills up this to the brink. What if I do this? No? Okay, let's try this. 11. So I don't want to see 5F22, but we do see 5F22. Well, let me just check this. So we're seeing how many A's do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 will fill up the block. If my math works correctly here, it will fill up the block. Let's just double check here. So this is going to be 12. Oh, sorry. This is actually when we get a new block. But what we got to do is start to repeat. Up here we got to start 9 A's. This is going to be much better. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9 A's. Because after 9 A's, we get this pattern here. That's when the block is full with A's and we see the repeating pattern. So if I were to do 9 A's, give it a tick, union all, select at version, semicolon hash, that would change the value that I want to change. There we go, much better. So now, we'll save that one for later in case we need it. So now I have this block here, and this block now contains very much 1, 2, 3, 4, 5, 6, and then 8 A's, or whatever, 6 plus 8, 14, 9 A's, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it contains a backslash. Next block contains SQL injection, union all select, etc. So what we need to do now, we need to take this and remove the slash. Now how can we remove the slash? Very easy. Because up here, this block represents this, no slash. This block will never change. It contains all A's and this unknown content. So we'll do this. Simply replace it like this. That's what we're gonna do. And it's hopefully gonna be applied to the backend as the backend expects, and allowing the backend to decode it, decrypt it, and basically run SQL injection on the database. So let's just split, let's remove the line feeds here. So we can join up these, and we need to do from hex. And now we got the binary. We do 2 base 64. And this looks good, but we need to URL encode as well. Eek. Okay, URL encode. Isn't CyberChef beautiful? It just saved me a lot of trouble because it contained the URL and everything and the parameters operations in the URL up here. Beautiful. So now we do URL encoding. Now let's send this into the search thingy. So let's find the search in the history here. Here we have search. So we replace the search query with this here. And we send. And what do we look at? What is this? That is not a computer joke, or you could maybe make it one, but it is actually the version number of the database. You can see it in the URL here as well. As long as the database receives this input here, it will actually show you the version number of the database now. Okay. So that proves SQL injection. We managed to remove the backslash. Next thing we want to do, password to the next level. Password to the next level. Where is the next level? Normally you would pivot into information schema, tables, columns, and so on. But this is already a long video, and I'm pretty sure that these levels store the password in users, and the column is just called password. Unless there's a challenge to actually enumerate the database, this is how they do it. So what we'll do is we'll do union, we'll do a tick, union, all select password from users, semicolon hash. This is going to be our input. And we'll go back to the repeater, force the encryption to take place, like from here. So this will force the encryption to take place. Now, there's no decryption yet, right? So we now make use of the web server backend as an oracle for us. So we're telling the oracle to, hey, encrypt this plain text for us, give us an encrypted string. And we are now using known plain text to force the encrypted string to become a certain piece of value. Now we take this here and we split it into blocks. So now we have the different blocks, and we carefully replace the blocks that we want to modify. So here, for example, we have, I think we're going to do this one. We take this one here and we replace the third block that contains a slash, just like we did before. And let's see what happens now. Put it in here. We have the encrypted string. Back to, well, we can do it here actually. Let's search here. We'll do it up here. And just like that, we got the password to the next level. Let's make sure actually. You never know. Pretty cool challenge. Natas 29. Yep, there's a level. There's the next level, which is going to be the next video, of course. So thank you, everybody. If you have any questions, leave them down in the comments. Leave a like if you like this, if you found crypto attacks and ECB to be interesting. And of course, if you want my updates on further videos, I do sometimes create videos. Just subscribe and you will probably get a notification. So thank you very much, and thank you everyone who has reached out and who have said hi and said that you love the content and so on, and who have encouraged me to produce more. You know who you are. Thank you all for doing that stuff. It means a lot to me. So that's it, folks. Bye-bye.